Yeah, I mean, I think 2 weeks after the classes have begun, you should know which meeting to join. Um, yeah, so please join the right meeting. Okay, so we'll begin. So the last time we were discussing about, we discussed a bit about determinants, and then we started discussing about norms. And today we'll discuss several properties of norms. Just a second. Yeah, so today we'll discuss several properties of norms. Recall, so that we have this right starting point, recall that something is a norm provided for any x and y belonging to this vector space V over which the norm is defined. The norm of any vector x is greater than or equal to 0, and it's equal to 0 if and only if x is 0. It has the homogeneity property, namely that the norm of c times x is equal to the magnitude of c times the norm of x for every c in this field F. And finally, the triangle inequality, norm of x plus y is less than or equal to norm x plus norm y. If property 3 is not satisfied, then we call it a pre-norm. And if property 1a is not satisfied, then we call it a semi-norm. Also recall the definition of an inner product. The inner product is defined like this. If it's defined from 2 points, you have to choose 2 points in V, and then it maps those 2 points to the field F. So given any x, y, and z belonging to V, the inner product of x with itself is non-negative, and the inner product is equal to 0 if and only if x is equal to 0. The inner product is additive. So if you have x plus y comma z, then that is x comma z plus y comma z. And it is homogeneous in the first argument, namely that cxz inner product is the same as c times xz for every c in the field F. And it's also Hermitian. If you exchange the order, you do inner product of yx, you get the complex conjugate of the inner product between x and y. So also we saw one crucial property, that if this some dot comma dot is an inner product, then x comma x power half, the inner product of x with itself power half, is a vector norm on V. So that's one crucial property that connects inner products to norms. So using any inner product, you can define a norm. Now, today we'll start by discussing some example norms. These are perhaps the most popular norms that are used in different applications. The most popular norm is the Euclidean norm, which is also known as the L2 norm, or more simply as the 2 norm. It's just the sum of the squares of the entries of x raised to the power half. So one important simple formula is that norm x square, this is called the L2 norm. So L2 norm of x equal to x transpose x. It's a very useful formula, and it gives you an algebraic way of writing this particular Euclidean norm. The Euclidean norm of x, the norm of x minus y, L2 norm of x minus y measures the Euclidean distance between x and y, meaning our conventional notion of length between x and y. The second norm I want to discuss is what is known as the L1 norm, or the sum norm. And this is also known as the taxicab norm, or the Manhattan norm. So the Manhattan area of New York is famous for having perfectly rectangular, the streets divided into perfectly rectangular grids. And so this essentially measures, if you're given a point A and a point B, you have to go, it's like this grid you see in the background here. So if you have a point here and another point here, the way you can go from this point to this point, you can go like this, or you can take a and go like this. But however you go, the total distance you will traverse is actually the same as long as you're going along the sides of this grid. And that is basically this sum norm. So it is equal to, it's written as norm xl1, and it is equal to mod x1 plus mod x2 plus etc. plus mod xn. The sum of the magnitudes of the entries in X. So a small exercise for you is to verify that this is in fact a vector norm. That means it must satisfy those 4 properties that we discussed just now. And another property is that it is not derived from an inner product. The third norm is what is known as the max norm, or the L infinity norm. This is also called the Cartesian norm. And this is written as x infinity. And the reason for the subscripts will be obvious in a second. It's the max of so it's the max magnitude entries of x, the largest magnitude entry in x, that is the norm. So one thing is that if you think about it, these are all different ways of measuring the length of a vector. And taking the sum of the squares and taking to the power half is one way to measure the length of a vector. And in a two-dimensional space, if I draw a vector, say like this, then the length of the vector is actually this squared plus this squared power half. We are just using Pythagoras theorem to say that's the length of this vector. And so it's a reasonable way of measuring the length of a vector. Similarly, the L1 norm, it's measuring the length you have to travel if you were restricted to go along the sides. And the L infinity norm essentially picks off the biggest entry in X in magnitude. And that's also, I can't give you an example of how that will be the length, but it's you can imagine that maybe the cost is completely dominated by the largest segment in one of the dimensions that you need to traverse, and therefore that is the L infinity norm. Um, However, for example, if I took the min here, the min of the magnitude entries of x, that is not a norm. Can anybody think why?
So is the second one where we are taking the min, is it due to the second property of positivity in the sense
Yeah,
that,
that is one. You can also show that yeah, so certainly positivity doesn't hold. If any one entry is zero, then this star is going to be equal to zero.
yeah,
And so it won't be zero only if all the entries are zero. Um, you can also probably show that it does not satisfy the triangle inequality. Um, that's also easy to show. So similarly, this when p is less than 1, this definition of LP norm, it does not satisfy the triangle inequality. So show this. Okay, show. So the triangle inequality for the LP norm um, for p greater than or equal to 1, it basically reads norm x plus y LP is less than or equal to norm x p plus norm y p. Again, it's something to think about. How do you show this? For any p greater than or equal to 1, if you define the LP norm like this, then it satisfies this triangle inequality. And this inequality is called Minkowski's inequality. Okay. So here in this inequality, if I substitute in this definition of LP norm, if I substitute p equals 1, then it is mod xi power 1 whole power 1. And so that reduces to the sum norm. And if I take p very, very, very large, then what happens is that when I'm taking mod xi to a very large power, and I'm adding them up across all the xi's, the largest magnitude entry in the vector x will completely dominate the sum, and therefore the value of the sum is equal to, as p tends to infinity, the value of this sum will be equal to the magnitude of the largest entry of x raised to the power p, and then I'm taking it to the power 1 over p. So this will lead to the largest entry in magnitude in x as the LP norm as p tends to infinity. And that's the reason for this notation, norm x infinity equals the maximum of these entries. So this p norm, it reduces, also when p equals true, it's the sum of the squares of the magnitudes of x, the entries of x raised to the power half, which is exactly the same as the Euclidean norm. So this is a generalization that includes the L1 norm, L infinity norm, and L2 norm as its special cases. So now also to just get a feel for how these norms look like, one can ask so you can look at a two-dimensional space and ask what is the locus of points that have a fixed norm. So if I take the L2 norm, if I take the set of points V such that norm VL2 equals 1 on the two-dimensional plane, what will it look like?
circle.
It's a circle. So assume that this is a circle and its radius will be equal to 1. And if I take the set of points such that V such that norm V infinity equals 1, so the norm is now the largest entry, and so basically what will that look like? If you are fleet-footed, you can think about it.
Square.
Square.
Exactly. So that will look like a square. So for any point along this line here, the largest, so whatever the value of y, the value of x is equal to 1. And so this is 1 and this is 1. Okay, and this is the origin. And for any point along this line, the x value is equal to 1. And so the infinity norm of any point along this line is equal to 1. Similarly, any point along this line, the L infinity norm is 1, like that. So that's how you get the square. And finally, if I take all the v's such that L1 norm of v equals 1, what shape will I get?
A line.
You'll get a, I mean, I'll just
Four
call it,
point.
yeah, I'll get a diamond. I'll just call it a diamond for simplicity. And these are points. This is point 1 comma 0, and this is 0 comma 1. This is the origin. So for any point along this line, the sum of these two coordinates is always equal to 1, and so that's how you get this diamond shape. So that's kind of the shape of these norms. And if I take the L3 norm or L4 norm, that will be like a circle that is further bulged out. It'll end up looking a bit like this. So it's not quite a circle, it's bulged out compared to a circle. So I'm trying to draw it a little more bulged out. So this could be like the, so that's how these will look. Okay. Now, what are norms good for? There are several things that they're good for. So I'll just give some examples. So one very important use is for showing convergence. So basically, for example, we know this formula that if I take 1 minus x inverse or 1 over 1 minus x, and I can write this as 1 plus x squared plus etc. It's an infinite series. Now, when is this true?
X less than 1.
X infinity, x to the power infinity tends to 0. Limit.
Exactly. So x mod x should be less than 1, and that is the magnitude of x should be less than 1. So this is true for a scalar, but suppose I wanted to find identity minus a matrix A inverse. And so when can I write it as I plus a squared plus etc. Now, obviously this condition here suggests that maybe we need a condition on somehow the size of this matrix A, and the answer is that this is true if a matrix norm on A, which I'm going to write with 3 lines. So going forward, I will use 3 lines to denote matrix norms. And I need to tell you in which norm I will use here. And it turns out that any matrix norm will do. And if you can find a matrix norm under which the norm of A is less than 1, then a formula like this can be used to compute the inverse of I minus A. And the other use is if you know that mod x is less than 1, you can actually bound how big the rest of the series will be. And in turn, you can determine how many terms you need to use in the summation in order to get a sufficiently accurate estimate of 1 minus x inverse. And similarly, the norm of A will tell us how many terms I need to include in this series in order to get a sufficiently accurate representation of I minus A inverse. And so in a more general sense, it's useful for determining how many iterations of an iterative algorithm you need to use to solve a certain problem to a desired level of accuracy. And in fact, the second use is more about quantifying the accuracy of matrix computations. And these are again things that we are going to look at later in the course when we look at stability of matrix computations. So suppose we want to find A inverse, but instead the entries of A are noisy, and so what we get to see is suppose A was equal to A naught plus E. And so what we've done is we've gone and computed A inverse, but what we really want is A0 inverse. Then we want to know what is the potential error that we've incurred by computing A inverse. So to find the error in computing A inverse, which is A0 plus E inverse, instead of A0 inverse. And again, the answer lies in the norms. And the third use is in bounding eigenvalues or perturbations of eigenvalues. So if you perturb a matrix by adding a small error matrix to it, how much will the eigenvalues get perturbed? And all of these, the answers lie in norms. So this is also something that we are going to see later in the course. Now, another thing is that we've seen a few kinds of norms, but the question is, can we come up with new norms based on existing norms that we know? And so, for example, these are you can do that, and these exploit some properties which are known as algebraic properties of norms. And I'll give two examples here. So the first is that if say x alpha and x beta are vector norms, then if I define norm x to be equal to the max of these two numbers, then this is a vector norm. Again, a property that's easy to verify. Okay, but you have to check that it satisfies those four properties of norms. Similarly, if this is a vector norm, say on C to the n, and T in C to the n cross n is non-singular. It's a non-singular n cross n matrix. Then if I define this so we'll call it the T norm, this is equal to the norm of Tx, then for any x belonging to C to the n is a vector norm. So you can produce lots of different norms. For example, you have a set of norms. You can take the max of any pair of them or any number of them, then you get another vector norm. Take any matrix T in C to the n cross n that's non-singular, then the norm of Tx gives you yet another norm. Obviously, the length of Tx is going to be the different from the norm of x. So in general. Okay, so in particular, for example, if I'm taking the Euclidean norm and if T is a unitary matrix, then xt will be equal to norm of x, but otherwise it need not be equal. Yeah. So we can produce lots of different norms like this, but another question is, where do we use these different norms? In particular,
Excuse me.
yeah, go ahead.
Do orthogonal matrices only preserve Euclidean norms or every norm?
What do you think?
Every norm.
No.
No?
Orthogonal matrices
Okay, okay.
preserve orthonormal matrices.
Yeah.
Okay.
Or the normal matrices. Will they preserve
These
every norm?
preserve Euclidean norm only, and the reason is very simple.
Because it is defined to be inner product, right?
Right. Inner product, in fact, what we call the usual inner product. So if I
Yeah,
write this square, it is equal to x transpose x. So which implies if T is orthonormal, then if I compute Tx, this is going to be Tx transpose. So this is bad notation. So this is Tx transpose Tx, which is equal to x transpose T transpose Tx. And T transpose T is the identity matrix for orthonormal matrix. And so this is equal to x transpose x, which is equal to x2 square. But for other norms, you can't write it like this. And so it's not true that it preserves other norms. So you can in fact ask, are there classes of matrices that preserve, for example, the L1 norm, or that preserve the L infinity norm? And in general, it's hard to find matrices that will, I mean, you can always find a matrix that will preserve the L1 norm or L infinity norm for a particular vector. But for any x, you cannot preserve its L1 norm or L infinity norm by multiplying it uh, by an n cross n matrix. So that's again something that you can try to show. So typically we use I was just discussing about where we use different types of norms. The reason why the L2 norm is the most popular norm is because it can be written like this. The L2 norm squared can be written as x transpose x, so it has lots of good properties. And so it's typical to use the L2 norm in optimization problems. Even if you want to use other norms, it's not uncommon to try to reduce it to an L2 norm and then solve a sequence of problems where you're working with the L2 norm and then hope that you will be able to solve the problem involving other norms. L1 norm is typically used when you want to find what are called robust estimators. And it's also used very heavily in compressed sensing, which I teach in the next term, and it promotes sparse solutions. Sparse solutions are solutions for these vectors where lots of entries of the vector are equal to 0. And many applications where you want to solve, for example, an equation like ax equals b, but suppose this has many solutions. You want to find the solution which has the maximum number of zeros in X. And for such things, solving for minimizing L1 such that AX equals B, this optimization problem will lead to sparse solutions for X. L infinity norm is useful when you want to, you care about element by element convergence or properties. However, as I mentioned, L2 norm is by far the one that is most amenable to optimization. So the norm in which the norm that is most natural to a given problem may not be the most mathematically convenient or tractable one. And so if you use a different norm to solve the problem, we want to, ideally we want to know how it is related to the original set out to solve. So for example, if you're considering a sequence of vectors and you want to look at, this is a sequence of vectors output by a particular algorithm. And if you monitor, say, the L2 norm of these vectors and you find that the L2 norm is converging, or you take the difference between consecutive outcomes of this iterative algorithm and you find that the L2 norm of that difference is converging, does it mean that the vector itself converges or not? So to answer these kinds of questions, there is a very strong property that norms satisfy, which is that um, essentially if a sequence of vectors converges according to a given norm, it in fact converges to the same point with respect to any other norm that you wish to use. And so, so I'll just discuss that aspect a little bit.
Sir, what is meant by robust estimation? Is it like should perform well in the presence of noise, or?
Yeah, certainly you want it to perform well in the presence of noise, but other norms also will give you good properties in recovery in the presence of noise. However, uh, what happens is that if you think about it, suppose I'll just go off to the side a bit here. This is a side note. So suppose you have a certain point x naught and you have an algorithm where you hope that the algorithm will return this optimal point x naught, but it returns a different point, call it say x hash. And now there is a distance between these two. And your algorithm is returning x hash because you've sort of said, I want to minimize, say, something like x, some function of x, subject to some constraints. And effectively, if you're looking at, say, the L2 norm, what this is doing is it's actually taking the difference between all entries of x hash and the corresponding entries of x naught. It's squaring them and adding them up and then finally taking a square root. So if I consider the square of this Euclidean norm, uh, you can see that if there are one particular pair of entries in x hash and x naught, where this difference is very large, because you are squaring it, the distance or the Euclidean norm will end up becoming a very big number. And so this really penalizes the most mismatched entry the most and penalizes the least mismatched entries less. But if you take x hash minus x naught and one norm, then what this is doing is just looking at the magnitude of the error between x hash and x naught. And so this essentially penalizes all the errors more or less equally. So that is what is called robust estimation. So you're not giving undue importance to incurring a large error in some components and incurring a small error in other components. All errors are equivalent to you. And that's what is referred to as robust estimation. So if
Yes,
there are
thank
many
you, sir.
parameters you can
Sir,
estimate.
yes, sir, but I mean, how does it translate in L infinity norm? There we are only optimizing with respect to only one, this maximum element, or how will it be?
You're looking in L infinity norm, you're looking at the largest entry of x hash minus x naught. So this is typically used in what are called min-max type of problems, where what you want to minimize is the maximum deviation across all entries between x hash and x naught. And when that is important to you, then you would use the L infinity norm. So, yeah.
Okay, thank you, sir.
So let me define what I mean by convergence of a sequence of vectors. So the main point, I'll first write down the punchline here and then I'll discuss further. So the punchline is that vector norms can be used to measure convergence of a sequence of vectors. So let me define convergence first. So let V be a vector space over R or C, and let be a vector norm on V. So we say the sequence xk. So this is a common notation for denoting a sequence. You write curly braces xk, and sometimes you write k greater than or equal to 1 if you want to say k goes from 1, 2, 3 up to infinity. This of vectors in V converges to x, which is also in V, with respect to this norm defined like this, if and only if xk minus x goes to 0 as k goes to infinity. And we will write this as limit k tends to infinity xk is equal to x. Now again I have to write with respect to this norm like this. Okay, so this is the definition, and two aspects sort of immediately come out. One is that it seems that in order to define convergence of a sequence of vectors, I need to tell you with respect to which norm I'm asking for this convergence. The second is that if I change the norm, it's possible that this xk will converge to a different point x dash, because it's dependent on which norm I'm specifying here. So the two related questions are, one is is it possible that this given sequence xk converges with respect to one notion of norm but not in another? And the second question is that can a sequence converge to two different points with respect to a given norm? Um, uh, so it turns out that the answer to the first question, to both questions, is no in finite dimensional space, but it is possible that a sequence converges with respect to one norm but not in another in infinite dimensional vector space. There is an example in Horn and Johnson which shows that a sequence can converge to two different points with respect to two different norms. But we won't discuss that here because the focus of this course is on finite dimensional vector spaces. So the first question is, can a sequence converge in one norm but not in another? And the answer is no in finite dimensional vector space. And we'll see why this is true in a minute. But before that, let me write the other question, which is actually easier to show. So, can a sequence converge to two different points with respect to a given norm? So the answer is no. So that is limit k tends to infinity xk equal to x and limit k tends to infinity xk equal to y with respect to the same norm possible? And the answer is no. And that's very easy to see, and I guess some of you might have already been able to figure out why. And the reason follows from triangle inequality. So if so what we are told is that xk minus x, this goes to 0 as k goes to infinity, and similarly xk minus y also goes to 0 as k goes to infinity. So what that means is that if I take the norm of x minus y, so that is equal to the norm of x minus xk plus xk minus y, which is less than or equal to the norm of, this is triangle inequality, xk plus xk minus y, okay, which both of these terms are going to 0 as k goes to infinity. So this itself goes to 0 as k goes to infinity. So, but the left hand side is greater than or equal to 0. And which implies that the norm of x minus y, so this is non-negative, and but this is a norm. So if this becomes equal to 0, it implies that x equals y. So it has to converge to the same point.
Sir?
Yeah.
Sir, a particular sequence can converge to different points if we take the norm different norms.
So that is what I want to show. Now to show that a sequence cannot converge to different limits for different norms, there's one other theorem that we'll need. And so this theorem is actually a theorem from real analysis. We'll outline the proof, but there is one step that we will need from real analysis, which I won't go into here. So let F1 and F2 be real valued functions on R to the n for n finite. And suppose three properties hold. First is that Fi, so Fi of x is greater than or equal to 0. So these we'll be replacing F1 and F2 with norms later on. So this is true for every x in R to the n, and Fi of x equals 0 if and only if x equals 0. And property B is that Fi of alpha x is equal to mod alpha times Fi of x for every alpha belonging to R and x belonging to R to the n. And property C is Fi of x is continuous on R to the n. Okay, so notice that I don't require the triangle inequality, which is part of the definition of a norm. I just need these three properties, but instead of, or not instead of, but I don't need the triangle inequality, but I do need this continuity property on R to the n. I will just leave it like this. I think all of you have some idea of what it means for a function to be continuous. I won't go into the definition of continuity and so on here. In fact, this continuity is really used only in when we use another famous theorem from real analysis called Weierstrass theorem, which is used in the proof. But other than that, let's not get into the notion of continuity in this right now. So we'll take this on faith that we know what is continuous and what it means for a function to be continuous. So when this is true, then for there exists positive constants which we'll call C small m and C capital M, such that C small m times f1 of x is less than or equal to f2 of x is less than or equal to C capital M times f1 of x for every x in R to the n. That means, now translating this into norms, what this is saying is that if you take a different norm, the norm of x with respect to this, the second norm of x is sandwiched between some constant times the first norm and some other constant times that same first norm. So that is this result. So the proof goes like this. So let h of x be defined as f2 of x over f1 of x. Okay, for x in some set S, where I'll define this set as S is the set of x in R to the n, such that x2. So I'm using the Euclidean norm here, but you can actually use any other norm here, it doesn't matter. So the reason, I mean, the only thing you need is that the set S must be a compact set, and it does not include the zero vector. Okay, so that's, again, this is another notion from real analysis that is beyond the scope of this course, but for your reference you can note that this is a compact set. Then what we have is that h of x is certainly not 0 for any x belonging to S, because there is the zero vector is not here, and phi of x is positive, strictly positive for any x not equal to 0. And so both these numbers are f1, f2 of x and f1 of x are both strictly positive numbers, and so the ratio is also some strictly positive number, and so h of x is not 0 for any x in S. And also h of x is continuous on x belonging to S because of this property C. The ratio of two continuous functions is also continuous. Okay. So now what Weierstrass theorem says, it says that h, a function h which has these two properties, it attains a finite positive maximum C capital M and minimum C small m on the set S. So that implies that we have C small m times f1 of x is less than or equal to f2 of x. So h of x is bounded between C small m and C capital M, and h of x is just f2 over f1. I'm taking f1 to the other side, and then I have C capital M times f1 of x for every x in S. But we have that if I take z over norm z, this it always belongs to S for every non-zero z in R to the n. So then what I can do is, if I want to show that this holds for every x, I just replace x with uh, x in R to the r. If I want to show that this holds for every z in R to the n, I'll just replace x with z over norm of z for any non-zero z. Then by property B, which is the homogeneity property, this norm z can come out of this, and then it will cancel throughout, because there will be a 1 over norm z here, 1 over norm z here, 1 over norm z here. It comes out throughout. So from B, the above inequality holds for every non-zero z belonging to R to the n. But then if z equal to 0, the case is trivial, because this is 0 and this is 0, this is also 0, so it's already true. So that concludes this proof. So now the consequence of this is that if you have two different norms, are vector norms on Rn, and if xk is a given sequence of vectors, then limit k tends to infinity, xk is equal to x with respect to alpha if and only if limit k tends to infinity, xk is equal to x with respect to beta. So it doesn't matter which norm you consider. If it converges with respect to a given norm, then it converges to with respect to any other norm, and in fact it converges to the same point. So the proof is one line. So we have by the previous theorem that Cm times xk minus x alpha is less than or equal to xk minus x beta. So there exist constants Cm and C capital M such that this holds xk minus x alpha, and this is true for every k. That implies that the xk minus x alpha can only go to 0 if and only if, see, this quantity is sandwiched, this quantity is sandwiched between these two quantities. So if you want this to go to 0, then this side will also go to 0, and that's only possible if this guy is also going to 0. If this is going to some non-zero quantity, then you can't have it being sandwiched between these two if this is going to 0. So this is true if and only if xk minus x beta goes to 0 as k goes to infinity. Okay, so basically this implies that in a finite dimensional vector space, all norms are equivalent in the sense that whenever xk converges to x with respect to one norm, then it converges to the same x with respect to any other norm. So I think we're out of time for this class, so we'll stop here and continue the next time. Any questions?